Yes, it's visible.
Alright. So we'll be doing configs today. So like I hope you all are familiar with this basic config in center extent lemma, but just in case, we'll go through the proof of it. So essentially, it says that if we have a triangle ABC, and its circumcircle, call it omega, and say the angle bisector of BAC intersects the circumcircle at L, then it says that like L is the midpoint of arc BC. Then it then it says that like L is the midpoint of arc BC not containing A. Can anyone prove this? Someone who hasn't seen it before, preferably. Okay, so it says that if I have the angle bisector of BAC and it intersects the circle ABC again at L, then L is the midpoint of arc BC not containing A. Can you prove this? Maybe I'll give you a minute. Preferably someone who hasn't seen this before. Okay, sure. Could you unmute maybe? Ayush, could you unmute? And since no one is saying anything, I'll just go ahead. So we want to show that L is the midpoint of arc BC. Essentially, that is equivalent to saying that LB is equal to LC, right? So we'd want to show that angle LBC is equal to angle LCB. And equivalently, we want to show angle LAC is equal to angle LAB. But that is known because AL is the angle bisector of BAC. Did everyone get that? Can people please unmute? Like, feel free to unmute in my class because, um,
Clear.
okay, sure. Now, can anyone show that if IA is the AX center, then BICIA is cyclic?
ICIA is 90, so is IBIA.
Sure, great. And can you show that L would be the center of the circle?
We had that BIC is like circumcenter is L.
Why is that?
Because already we have that LB is equals to LC
And so why does
and like angle chasing gives LI is equals to LB, like if we connect IB.
sure, yeah, you can say that like angle LIB is 180 minus angle BIA, and you can prove that it's equal to angle LBI. It's not very difficult. I'll leave it at that. We've got some more configs to do. So the next config is known as Reyaansh theorem. Um, I'll just put it up here. So um, what it says is that if I have two circles that intersect at A and B, and I have a line passing through A and another line passing through B, and say these two lines intersect the first circle at P and Q, and the second circle at R and S. It says that RS is parallel to PQ. Can anyone prove this?
Angle ARS is equals to angle ABQ, which is equals to 180 minus APQ.
Great. That works. Angle ARS equals angle ABQ equals 180 minus angle APQ. Honestly, Reims theorem is something that it's kind of like a config that you wouldn't really write in a write-up. Um, it's something you wouldn't write in a write-up, but it's more of a config that you should know so that you can recognize it in a diagram. So I would not recommend writing this in a solution because it's basically just a two-step angle chase. But it's good to know if you can recognize it in a diagram. Um, one I hope everyone's got James' theorem. Next, we'll go to the more non-trivial configs. So the first one is Simpson's line. It's a more well-known config, but we're still going to cover it because it's very well-known and it's very important as well. So I'll not draw it out here because I'm incapable of drawing. But what it says is that if I have a triangle ABC and a point P that is cyclic with this triangle, and I draw the feet of perpendiculars from P onto the three sides, then it says that the feet are collinear with each other. Can you prove this? So I'll give you maybe 2 minutes or so. I think the diagram is not very clear. Um, is the diagram like visible? Like, can you read stuff on it?
Yes,
Yes.
clear, clear enough.
Okay. So does anyone have any idea?
Yes, like there are a lot of cyclic words here. So ADPE is one, and so is PEFC.
Okay, so ADPE is cyclic. You say why is that?
There are two 90 degrees oppositely located.
Okay, and PEFC is cyclic similarly. Okay. Great. So then why does that show collinearity?
Like PEF angle, we need to show that this angle DEF is 180.
Yes.
So we can break it down. So one part is DEP and the other is DEF. So DEP is equals to PCF. We
Okay.
need to show this like DEP is equals to DAP by cyclicity,
Yes.
and PEF is equals to PCF.
Okay. So you're using directed angle.
Yes,
Okay.
and both are equal since the since ABCF is CP is cyclic.
Okay. Right. D E E E and B. Okay. So yes, so essentially what he said is correct. So DAEP is cyclic and PEFC is cyclic. So we get that angle PED. Sorry, I'll just fix this. Right. So angle DEP is equal to angle DAP by cyclicity, and DAP is equal to angle BAP, and BAP is equal to angle BCP. And by cyclicity again, BCP is equal to FEP. So DEP is equal to FEP, and we're done. So that proves that DEF is collinear. Now what we're going to do is we're going to draw the orthocenter of triangle ABC. So now we claim that PH is bisected by the Simpson line. Basically, like if the Simpson line, basically the Simpson line intersects PH at its midpoint. Can you show this? Okay, firstly, what we're going to do is we're going to mark this intersection. The intersection of the perpendicular through P to BC and the circumcircle. So we're going to call this X. So can you show that AX is parallel to the Simpson line? Yeah, X is actually the point of intersection of the perpendicular from P and the circumcircle.
Angle AXP is equal to ABP, and that is equal to ACP, and that is equals to EFP. So we're done.
It's equal to ACP and it's equal to EFP. So you're done. Yes. So AX is parallel to the Simpson line. So I'll call the Simpson line as SP. Okay. So now we have that AX is parallel to the Simpson line. Next, can you show that if AH intersects the Simpson line at L, then LAX F is a parallelogram?
LA and FX are already parallel.
Yes. Therefore, LAXF is a parallelogram. Okay. Now, if I reflect X about BC, um, so I'll call this X prime. The X prime is the reflection of X about BC. Can you show that X prime is the orthocenter of triangle PBC? Yes, that's right. Yeah, the reflection of an orthocenter lies on the circumcircle. Yes. So X prime is the orthocenter of triangle BBC. Um. So now I'd like you to show that AH X prime P is a parallelogram. Okay. So to help you with this, I'm going to draw in the reflection of H about BC. So can you say anything about AP HX?
Can you repeat?
So I've drawn in the reflection of H about BC. So can you say anything about quadrilateral AP X H prime?
It is a isosceles trapezium.
Yes. So now if I reflect H prime X about BC, I get HX prime. So can you say anything between HX prime and AB? Sorry, AP.
They must be parallel.
Yes, exactly. So AP is parallel to HX prime. Now, can we say anything about quadrilateral AP X prime H?
It is a parallelogram.
Yes, exactly. AP H X is also a parallelogram. Okay. Now, can you show that can you show that LHPF is also a parallelogram? This would directly imply that PH is bisected by the Simpson line. So can you show LHPF is a parallelogram?
We can do it like we know that LAXF is a parallelogram, and so is APH X dash H, and therefore like a LH is parallel to uh like PX dash, and
Yes.
the side lengths are equal, like opposite sides are equal.
LH is parallel to PF, sure.
And the opposite side lengths are equal by
Ah, yes.
parallel.
Yes. Okay, just give me a second. Right. So now this implies that LHFP is also a parallelogram, right? Now, what does this mean? This means that LF bisects PH. right? But LF is just the Simpson line. This means that the Simpson line bisects PH. Okay, this is another important result to remember with respect to Simpson line. Okay, so has everyone got it? Did everyone understand? And does anyone have any doubts? All right. So now we can actually do a problem. Um, so the problem, I'll just paste the problem. Give me a second. Is the problem visible? Hmm. Hello? Okay. So the problem is here. And I'll just put up a picture because I cannot draw. Um, Give me 1 minute. So I just put up a computer generated picture because I cannot draw, and plus you this will allow us to see like all the details in the diagram immediately. So when we're solving this problem, so ABCD is a cyclic quadrilateral, right? And AC is perpendicular to BD. And now E is the reflection of D about AB and F is the reflection of D about BC. Now EF cap BD is P. And immediately what can we say about P?
PZ is equals to ZD and PZD are collinear.
Um, yes, sure. Yes, PZ, are collinear. But is there anything else we can say? Remember that E is the reflection of D. Remember what we just proved.
I said PZ is equals to ZD.
PZ is equal to ZD. Yes, sure. But let us try to prove something before that. That's true. I think that's true. Yes. But can we try and prove something before that? I remember what we just proved. Keep what we just proved in mind. Mm,
P is the orthocenter.
yes. Yes. P is the orthocenter of triangle ABC. How do you prove this?
Because like this line XZY must bisect this DP, I mean DH, and also we have that DZ is perpendicular to AC, so it must be the like the
Yes. By Simpson line, DZ is perpendicular to AC and XY will bisect DH, so P must be the orthocenter. Great. So we have P is the orthocenter. Right. So we have figured out what P is. Now, can we try and figure out what Q and R are? Okay, sure. Reflections of P. How would you prove that? Okay, yes, yes. How do you prove that? Can we like say something about circle DPE with respect to line AB? In fact, how does line AB relate to the segment DE? Why does AB bisect PQ?
Like AB is the perpendicular bisector of DE
Sure.
and once.
So what happens if AB is the perpendicular bisector of DE? What can we say about circle DPE?
This circle has the center A.
No, not necessarily. Why would that? It looks like it, yes.
No,
And
like
I suppose it might be yes.
AB is the perpendicular bisector of DE and AZ is the perpendicular bisector
Okay,
of
yeah, yeah,
DP.
sure. A is the center, my bad. A is the center of circle DPE. Okay. So then, what can we say about Q? Okay, like, and you see that like circle DPE is symmetric about line AB, right?
Yes.
So now, like, the reflection of P would lie on a circle DPE, right? the reflection of P about AB. But since P is the orthocenter, the reflection of P about AB also lies on the circle ABC.
Yes.
So that's got to be Q. Did you get that?
Yes.
So that means that PQ is perpendicularly bisected by AB. Is that clear? So in fact, we get EQPD is an isosceles trapezium. So EQ is equal to PD. EQ. So PQ is parallel to ED, but PQ-ED is cyclic, right? So EQ equals PD and similarly PD equals RF. Yes, that's right. So EQ equals RF. So we're done. So we have that like
How do we see that PQ is parallel to D?
because so note that AB is a perpendicular bisector of DE. Yes.
Yeah.
So that means that the circle DPQE is symmetric about AB.
Yeah, makes
Yes.
sense.
So now that means the reflection of P about AB would lie on would lie on the circle DPQE.
Yeah, I got it. Makes sense.
But P is the orthocenter, so it's got to be Q. So that means EQ equals PD. Um, and but PD is similarly equal to RF. And so we're done. Yeah, exactly. Okay, great. So now we can go to the Iran lemma. I will just put that in. So what the Iran lemma says is that if I have a triangle ABC and its incircle and say its touch points on the sides BC, CA, AB are respectively D, E, and F, and say the incenter is I and the midpoints of AC and CB are N and M respectively, then it says that EF, BI, and MN concur at a point. So if someone hasn't seen this before, can you prove this? Otherwise, if you've seen it, you can give the proof. Okay, I'll give some time. Okay, could someone say the proof? Sure, someone got the proof. Yes. We can angle chase to show that KEIDC is cyclic. And from there we can show that KM is parallel to AB. So the idea would be, so to show that KEIDC is cyclic, you just have to show that angle KEC um is equal to angle KIC because EIDC is already cyclic. And this is simple by an angle chase. And again, you can show that KM is parallel to AB by another angle chase. So the steps in this theorem would be to show that KEIDC is cyclic, and then you show that Km is parallel to AB. This would show that K lies on M. Okay, great. So we're done with the Iran lemma as well. So the Iran lemma first arose in the I think in the Iran TST Team Selection Test 1999. Problem 9. You can try it out if you want. I think it's in the EGMO as well. So you can try that out if you want. Okay, so now we'll do the last config and then we'll just do problems for today. So this config is known as 3 tangents, but we're not using it today, but it's also a good config to know. So I'll just draw it. So you have a triangle ABC and you have the feet of perpendiculars from B to AC and C to AB. And you consider the circle AEF. Note that since AFH is equal to 90 and AEH is equal to 90, we'd get that the orthocenter also lies on this circle. What the theorem says is that if M is the midpoint of BC, then ME is tangent to the circle, so is MF, and also the line through A that is parallel to BC is also tangent to the circle. Can anyone prove this? I believe this is also a problem for me, KMO, but just
The center lies on AH.
yes, the center does lie on AH.
It's the midpoint of AH.
Yes, it's true. And why is that? It's because angle AFH is 90, right?
Yes.
Great. I think I can do
That
that. Right.
proves the A parallel BC line to be tangent.
Yes, exactly. Because AH is perpendicular to BC, we can see that the angle made by the tangent through A and AH is going to be 90 degrees because AFH is already 90 degrees. Now, how do we show that ME is equal to MF?
BFEC cyclic.
Yes. Yes, correct. BFEC is like that. Okay. So, okay. What next?
So BC's diameter so implies or M is midpoint.
Yes. So MF is equal to ME. Now, how do we show that these are tangent to the circle? Note that it is sufficient to show that one of these are tangent because the others are equal. Okay. Okay, so MBE is equal to MEB equals 90 minus C. So how does that finish? Yes, exactly. MEH is equal to HAE. So that finishes by tangent chord. What is right? So we get that. So trivially, the tangent through A is parallel to BC. We got that already. Now BFEC is cyclic. So since the midpoint of BC is the center of the circle, MB is equal to MF is equal to ME is equal to MC. So it suffices to show that only one of MF and it suffices to show that one of MF and ME is tangent to this. And so the way we do it is angle MEB is equal to angle MBE is equal to angle HAC. And so by tangent chord, you're done. Great. So that basically just finishes all the configs we're covering today. So now we'll just do a, okay, so we're going to do one more config, but I just put it in the form of a problem. I'll just put it up here. I'll also put up the diagram. Right. So what can we do with this? So we have a circle and we have a chord AB and M is the midpoint of arc AB, and we consider a circle in the other segment which is tangent to AB and the circle, and the tangency points are K and T. We want to show first of all that T, K and M are collinear. First of all, I'll draw in the center of the big circle and I'll call it O.
TP and O must be collinear.
Yes, because of tangency. So T, P, O are right. TPO are collinear. What next?
And PK parallel to OM
Why is that?
because PK and OM are both perpendicular to AB.
Okay, great. So OM is perpendicular to AB, which is perpendicular to PK. Great. So PK is parallel to OM. Can we do something from here?
Also, TPK and TOM are both isosceles triangles.
Yes, exactly. That's the point. And now what can we say about those two? How do they relate to
So
each other?
they are similar.
Yes, exactly. TPK is similar to TOM. Now, how can we finish the first part?
Yes, like so TK must be collinear since PK is parallel to OM and TPO are collinear.
Sorry, could you repeat?
Like TP and O are collinear and PK is parallel to OM and they are similar, so TK must be collinear by Thales or something.
Right. That's correct. So now there's another way to do this. Using a homotherty. So since TPO are collinear, there exists a homotherty there exists a homotherty through T that takes P to O, right? And now since T lies on both of these circles and P and O are the centers of both of these circles, that means this homotherty takes the small circle to the big circle. Did everyone get that?
Yes.
And since like K is kind of like the bottom point of both of these circles, like the south pole of both of these circles, that means they would map to each. That means K would map to M under this homotherty. Is that fine? Now, since K maps to M under a homotherty through T, that means T, K, and M are collinear. Was that understood?
Yes.
Okay, great. Now we'll show that the power of M with respect to the small circle is MA square equals MB square. How can we show this? I just move a bit.
So MTB, this angle is MAB, and that is MBA. So since TKM are collinear, so TBM is similar to BKM.
What did you say after MTB equals KBM?
Then TKM are collinear, so like TBM is similar to BKM.
Okay. So since TKM are collinear, we get that angle TMB is equal to angle BMK. Right. Sorry, KMB, whatever. And this would give us that triangle TMB is similar to triangle BMK. Is that right? Yeah. So that gives us that triangle TMB is similar to triangle BMK, but now the power of B with respect to the circle is, sorry, the power of M with respect to the circle is MK into MT, right? If I just go back up, it's just MK into MT. So that means like MK, by the similarity we get MK by MB is equal to MB by MT, and therefore the power is equal to MK into MT, and this is equal to MB square. Did everyone get that? Okay. All right, just give me 1 minute.
Can you explain homotherty again?
I'll explain the homotherty. So if you look at the figure, since the two circles are tangent to each other, we get that there is a homotherty through T taking P to O, right?
Yes.
Now, since P and O are the centers of these two circles, we get that like the same homotherty takes the small circle to the big circle.
Right.
Right. And now notice that K and M are kind of like the south poles of these two circles, right? The tangent through K is AB, and the tangent through M is parallel to AB, right?
Yes.
The bottommost point of the circle. So that means that under this homotherty, K would be mapped to M because it's at the same position with respect to the other points. Is that fine?
Okay.
Like the idea is that PK is parallel to OM, and a line under a homothéty, the new line becomes parallel to the old line. That's the main reason. Did you understand that? Uh, like the idea is, if I take a homothéty through T and I have a line here, then the new line will be parallel to the old line. But PK is perpendicular to AB and OM is also perpendicular to AB. So PK is parallel to OM, which means that since K lies on the circle, that means that PK will be mapped to OM, and so K will be mapped to M. Is that fine?
Yes.
So that means since the homothéty maps K to M, we get TK and M are collinear. Okay. So we have about 20 minutes left. So we'll just do like one or two problems, and then we'll leave. Okay. So here's the problem. Give me 1 minute. I think you can like start drawing the diagram. I'll just put up the diagram in a minute. Okay. So has everyone understood the question, or shall I just go through it once? Anyone? Okay. So we have a triangle ABC, which is inscribed in a circle. And a circle and a smaller circle is internally tangent to the circumcircle at A, and it's also tangent to line BC at D. Now AB and AC intersect the circle again at P and Q. So they're marked over here. And now M and N are points on line BC such that MB equals BD. So basically M is the reflection of D about B. And similarly N is the reflection of D about C. Did everyone understand till that? Okay. Now lines MP and NQ intersect at K, and they also meet the circle again at I and J respectively. And also KA meets the circle IJK again at the point X. And we have to show that angle BXP is equal to angle CXQ. So it's difficult. This angle and this angle are equal. So how do you show this? Okay, just keep in mind the configs we've learned till now. So we've learned the shooting thing, the Death Star lemma, which says that the line AD bisects the arc BC, right? We just covered that above over here. So essentially, like if we isolate this figure, like we just have, I'll just draw it. We have a circle and a triangle, and we have this circle as well. And it's tangent to this big circle at A, and these 2 points are B and C. And this tangency point is D. What can we say about this intersection? In particular, what can we say about line AD? We just covered this configuration over here. Anyone?
AD bisects the arc.
Yes, exactly. AD is the angle bisector of BAC. Right. Now, do you notice something in this diagram? Something like that relates PQ and BC.
They look parallel.
Yes, exactly. And why is this true? One second. Right. So why is PQ parallel to BC?
Like the homothety thing.
Yeah, exactly. There's a homothety at A mapping PQ to BC. Another thing is, it's just Reims theorem, right? I mean, BP passes through A and CQ passes through A, and A, like you can consider like A is both the intersection points of the circle APDQ and ABC. So like in some sense, this is the degenerate case of Reims theorem, uh, where both intersection points coincide with each other. Like basically like the two circles are tangent. So that is why PQ is parallel to BC, and you could also, and I would encourage you to just do the angle chase. Here, um, we'd have, like if we draw the tangent at A and say this is some point, I don't know, L, then angle LAC is equal to angle APQ. But angle LAC is also equal to angle ABC. So APQ is equal to ABC. Right? So PQ is parallel to BC. So we have till now that angle BAD equals angle DAC. We also have PQ parallel to BC. Okay. What can we do now? Like just look at the diagram for a bit. I'll just move to the diagram. So just look at the diagram. What can we do now? Do any points look collinear or do any points look cyclic? Like that's like in a geometry problem, and once you draw the diagram, you should keep looking for collinear and cyclic points. That's one very good strategy. So do any points look collinear here? Like that are not already known to be collinear? AKD are collinear. Okay, sure. Can you prove that? APQI APQI looks cyclic, but APQI is already known to be cyclic. I is defined as the second intersection of MP with APQ. Okay, sure. Does anything else look cyclic? Something that we do not know yet. IJMN cyclic. Yes, IJMN is cyclic. Okay, why is that?
By the parallel condition.
Yes, Reims theorem. Yes, precisely. Um, but can we prove something else as well? In fact, we have a simpler proof. Um, like for parallel, the parallel condition works. Yes, because JIM is equal to JIP, which is equal to JQP, which is equal to JNP. So I'll just move and write that out. Oops. Um, what was it? JIM equals JIP. Right? JIM equals JIP is equal to JQP equal to JNM. Therefore, IJMN cyclic. Okay. What other cyclic quadrilaterals can we see? Maybe given the parallel condition, you can try doing a few angle changes and see what comes up. For example, how do we handle angle, say, ACM? AICM is cyclic. Why is that? Can you prove it? Maybe it would be better if you unmute because the class would be a little more interactive. Yes, that works. AIM is equal to yes. So I'll write that as well. Angle A equals angle P equals angle ACM. Therefore, AIC. Is there anything else we can say that is cyclic? Like similarly, if MAIC is cyclic, is there anything else we can say is cyclic? AJBN, yes. Similarly, AJBN is cyclic. Right. So we have this now. Now can we try and prove that AKD are collinear? Fine. Radax. What do you do with Radax? How can you show? Maybe unmute and uh, first of all, like which circles would you consider for Radax? I mean, considering we have three circles, it should be fairly obvious. But like, if we consider AICM and AJBN, sorry, AICM and AJBN, clearly A lies on the radical axis. But what other point lies on the radical axis? Like, if I'll just draw the circle, maybe it'll become clear. A, I, A. And okay, this was a bad circle. Okay. So like, what point do you think lies on the radical axis?
X center.
Okay, sure. Any other point that's like already drawn in the diagram?
D lies.
D lies. Sure. Can you prove it? Can you
Yes,
prove that?
like MB is equals to MD. So like the power of D with respect to the right circle is dB into dn, that is 2 into dB into dc, and so with the left circle it's dm into dc, that's 2 into dB into dc, both the same.
Precisely. So like we get that dm into dc is equal to dB into dn, and therefore D also lies on the radax of AICM and AJBN. Okay. Okay. So now how can we prove that K lies on AD? Any ideas? Like what circles do we have till now? We have AICM, AJBN, and MJIN.
We can use similarity and prove that ki into km is equals to kj into kn.
Yes, yes. You can also, yes, this like another way to say that would be that MJIN is cyclic, we know that, and K is the intersection of diagonals. So by radical center, K lies on AD, and so on.
Yes.
So yes, that was correct. That's true. KJM is similar to KIN, right? And so K lies in the radical center. So you're done. Okay, great. So okay, so I M A J B N and MIJN. We can just do radax on this, and so A, K, D are collinear. Okay, so now we have AKD collinear, and we have these couple of circles. Okay. Okay, so how do we handle X now? Is there any way we can handle X? Maybe we can look for some collinearities or maybe some cyclic quadrilaterals. Okay, I'll show the question. Maybe you can take a screenshot. All right. Okay. So how can we handle X? Can you look for some cyclic quadrilaterals? Maybe I can show you. Okay. So can we look for some cyclic? You know what? I'll just delete these circles because we don't need them right now. Okay. So what are some cyclic quadrilaterals through X?
XAQN.
XAQN. Okay. Yes. That could be, yeah, that is cyclic. Yes, I think so. Wait,
No,
why
wait 1 second. No.
cyclic?
Sorry.
Okay, that's fine. That's fine. Anything else? Maybe we can try and incorporate D as well. Okay, any ideas? Okay, like another way to approach is just you can just like try and do some angle chasing. Like just do some angle chasing and figure out some cyclic quadrilaterals. So like what quadrilaterals look cyclic here? Using X and D.
XJDN and XIDM.
Sure. And why are they cyclic?
Like again, JXK is JIK and that is JNM,
JXK is
JND.
IK. Sure, yes, that works. So JXK, so if I understand what you're saying, JXK is equal to JIP, which is equal to JQP, which is equal to JND, right?
Yes.
Okay. So now angle JXK is equal to angle JIP JQP equals J and D. Therefore, JX and D cyclic, and similarly D is also cyclic. D. Okay, so JXND and IXMD are cyclic. Okay. So now how do we handle X with that? Remember our configurations. What have we done? We have a lot of circles, so that should motivate one particular configuration.
A is the midpoint of XD as angle NXD equal to angle NJD equal to angle QAD, which
And
gives
I'm sorry.
AC parallel to NX.
Sorry, could you repeat?
AC parallel to NX as like angle NXD equal to angle NJD equal to angle QAD, which gives A is
Yes,
the midpoint of XD.
yes, that's true. Okay, I'll just move this figure. Yeah. So angle NX what? Angle NXD is equal to angle NJD by the cyclicity. And then NJD is equal to what? QAD. And that's equal to like CAD. Therefore, NX parallel to AC. Okay. But now C is the midpoint of DN. And therefore, A is the midpoint of DX. Right? So now this lets us delete like most of the points in the diagram. For example, I think we don't need J and I anymore. Okay, I can't delete any points in the diagram because the points are already there, but we do not need J and I anymore. And now, how do we continue from here? We want to show that BXP is equal to CXQ. Remember that. Um, I'll just write it out somewhere. Okay, this is our goal. And we have that A is the midpoint of XD. Now what do we do? So like, can we look for more a cyclic quadrilateral? That would, like, this is always a good strategy. Just keep looking at the diagram, keep looking for some cyclic quadrilaterals. It helps a lot. So can we look for some cyclic quadrilaterals here?
Can we prove XAQN cyclic?
XAQN. I don't think XAQN is cyclic. I think that was suggested earlier as well. I'm not very sure though. Maybe it can be proved. Like X and D are right now the most important points in the diagram, right? Can we look for some more cyclic quadrilaterals with them? Okay, XBDQ and XCDP. Okay, so how do you prove, for example, that XBDQ is cyclic? Okay, so to prove that XBDQ is cyclic, so like what are the most, like which angles can we handle here in XBDQ? Um, we can try to handle BXD, right?
But then we also need BQD.
Yes. So like how can we find those angles? How can we show that they're equal? We can't really do any angle changes with BQD, right? So what are the other ways of showing equal angles?
Like QDC is equals to QXB.
QDC equal to QXB. Why is that? Oh, we want to show this.
Yes.
Okay, sure. What is that equivalent to?
QDC is equals to QAD.
Q. Yes, QAD. Okay, yes. Yes.
But then we are stuck.
Yeah. Okay. To show equal angles, like what are the different ways of showing equal angles? One way is just normal angle chase. Another way is using similar or congruent triangles, right? So do any triangles look similar here?
AXB and AQX must be similar.
Sorry, could you repeat? A, X, B, and
AQX.
okay, AXB and AQX. Why is that?
No, like they must be. I don't have a proof.
Oh, okay. Anything else? And something we can prove? Is there anything we can prove? Like, forget about X for now. Just look at similar triangles in the rest of the diagram. What do we have? For example, is ADB similar to AQD? Um, Anyone? Is it similar?
Yes.
Yeah, exactly. ABD is similar to ADQ because first of all, AD is the angle bisector and ADB is equal to AQB. So they've got to be similar. So um, a triangle ADB.
That means AK is the angle bisector.
Yeah, we knew that already. AD was the angle bisector
Oh,
and
yeah,
AQB
yeah.
is similar. It's fine. We have XM parallel to AB. Can we do any similarities with that? Like note that triangle DXM is similar to triangle DAB, for example. Right, that's just parallel lines. So can we look at triangle BXM, for example? Is it similar to anything else? After ABC, what do we do? Like we have this pair of similar triangles, right? So now angle ABD, that's ABC. ABD would be equal to angle XDQ, right? So XMB is similar to XDQ. Sorry, XMB is equal to XDQ. And does that do triangles XMB and XDQ look similar? Anyone?
Yes, they must be similar.
Yeah. Why? Because we have XMB equals XDQ already. Uh, can we do anything with length ratios? Like we'd get that what? Sorry. BM over MX is equal to DB over 2AB, 2AB, which is equal to
Shouldn't it be like DQ over 2AD?
sorry. Yeah, we're coming to that because DB by AB is equal to QD over DA. Right. But 2DA is equal to DX.
So they are similar.
Yes. So triangle XMB similar to triangle XDA. D, Q. Yeah. Okay. So can we do anything with the triangles? Some other similarity. We also get that triangle XNC is similar to triangle XDP similarly, right? Now what? So someone said earlier that triangle AXC is similar to triangle CDP. Can you prove this? In fact, let's assume that triangle AXC is similar to triangle CDP and let's see what happens. If AXC is similar to CDP, then angle CDP is equal to angle CDP would be equal to what? Angle CAX, right? What happens there? Well, we're running out of time as well. Like we're already almost 20 minutes past time. So like, shall I leave this as homework or something, and maybe you can upload your solutions um on the OMC server, or do you want to finish this here? Oh yeah, you're down. Okay. Um. So I would say like don't start with problems of this difficulty. Maybe like you can like have you finished EGMO?
Hello,
Only
Bhaiya. I have done only first chapter.
yeah. So like just continue with the book. Try like go as far as you can. But like try to understand everything properly and solve like as many problems as you can. That would help a lot with geometry. Don't
Uh,
start with problems of this level. Just do the problems in EGMO. That helps a lot.
Bhaiya, and I have beautiful journey. That book also.
Yeah,
Should I focus on only one?
I would yeah like if you have that book then focus on that book because like that is also a really good book in my opinion.
Oh, okay. And for number three,
Do you have elementary number theory by
no, I have wo Aditya Khurmi, like that one.
yeah that's a very good book. How like you can study that as well. That's a very good
Uh, and when like I am stuck in concept of modular arithmetic, like is there any YouTube